All right, in section 5.2, we introduced the binomial distribution. If you recall, binomial distribution is a probability distribution in which there's a finite number of trials, only two possible outcomes, a success or a failure. Each property is done independently and under the same conditions, and the probability of success and failure in a single trial is the same as the other trials. And then the purpose of these distributions is to find the probability of a certain number of successes or a certain number or fewer successes out of a fixed number of trials. Here we're going to talk about a few additional properties of the binomial distribution, what it looks like on a histogram, as well as how to calculate expected value and standard deviation on a binomial distribution. So we'll start with how to graph a binomial distribution. So you have on the x-axis, instead of using values of x, you're using values of r, because remember, that's the number of successes that we want. Their probability goes on the y-axis. And then we'll have a bar going over each r value extending from r minus 0.5 to r plus 0.5. So this is where it's okay for your x values, or your r values in this case, to be in the middle of the bar. And of course, your height of the bar is going to be P of R. So here's an example. Jim enjoys playing basketball. He figures that he makes about 50% of the field goals that he attempts during a game. Make a histogram showing the probability that Jim will make 0, 1, 2, 3, 4, 5, or 6 shots out of 6 attempted field goals. All right, so again, this is a binomial experiment. You have a fixed number of trials. In this case, it's 6. Each trial is done under the same and are independent of each other. And then of course there's only there's only two potential outcomes of each trial. Either he makes the shot or he misses the shot. Problem says he makes about 50% of the field goals that he makes. So P is 0.5, which means that Q is also 0.5. Just subtract P from 1 and you get your Q. So here is your R, and now we just need to find the P of R, values of P of R. Now this we can easily do with our graphing calculator, just like we did in 5.2. If we're looking for exact numbers, this is a binomial probability distribution function, so binomial PDF. So we'll press, and if you want to fill this out easily, you can also do this in your graphing calculator in the graph portion by pressing y equals in the upper left-hand corner. We're going to, in one of our equations, we're going to press second variables to get our distribution menu. Scroll till we find binom PDF. We'll click that. Our trials, there are 6 trials. Our value of P is 0.5, and for the X value, we're going to put X in its place. So that way we can easily find on our chart each P of R for each value of X. So we'll press second. Actually, no, before we do that, we're going to press paste to make sure that it goes in our function. Second graph, and then there we go. Those are each of our probabilities. So here we rounded to 3 decimal places, so I'm going to do that here as well. The first 3 are already done. So that means that when R is 3, this is 0.313. This is 0.234. This is 0.094. And this is 0.016. So there's our probability distribution. Let's go ahead and put this into, let's go ahead and apply this to a histogram. Okay, so our first value, 0, has a probability of 0.016. So this is like right at the bottom here. So we're just not going to even make this very large at all. Then our value of 1 gets a value of 0.94, so almost at 1, but not quite. We're going to make sure that our probabilities land in the middle, or that our values of R land in the middle. 0.234, that's about, we'll say right here. Then we have values of for 3.312, that's right above the 3 mark. And I know my graph is not going to be the smoothest. And then it looks like 4, 5, and 6 have the same values as 2, 1, and 0 respectively. So we're going to mirror this here. And I'm going to mirror this here. And then I'm going to mirror that here. Right here. So the best I can, as best as I could, this is the histogram for our probability distribution. How would I describe this? Well, it's very much mound-shaped. It's very much mound-shaped symmetrical. And we're going to find that as our probability gets closer to 0.5, see, here the probability is exactly 0.5. So because the probability is exactly, the probability, and I mean the probability of each trial, because the probability, the lowercase p, of each trial is exactly 0.5, you have an exactly mound-shaped graph. But you'll find that as the small p goes either smaller than 0.5 or larger than 0.5, that's where we start to see some skewness. So let's try here this example. About 60% of cancer survivors are ages 65 years and older. You randomly select 6 survivors and ask them whether they are 65 years of age and older. So here, either they are 65 and older or they're not. So that is, again, another binomial experiment. So I have 6 survivors, which means I'm going to have 7 specific values of x. 0, 1, 2, 3, 4, 5, 6. My probability of success, P, is 0.6, because it's about 60%. Our N was 6, and then our R will just be X as before. So again, I'm going to fill this out using my graphing calculator. So this is a binom PDF, 6. This time 0.6 is going to be our P, and then our R will be X, second graph. All right, now I'm going to start filling these in. Again, I'm going to go 3 decimal places. 0.04, I'm sorry, 0.04, I should say. 0.037, 0.138, 0.276, 0.311, 0.187, and 0.047. Okay, so let's go ahead and apply this to our histogram, starting with 0.004. Again, I'm not going to make this first bar very tall at all. Then 0.37, so we're going to make this a little bit taller, or 0.037, I should say. 0.138, almost about halfway, but a little bit less. Go right here. 276, so about right here, we'll say. And again, I'm just kind of eyeballing it just a little bit. 311, right here. Clean this up a little bit. 187, so about right here. And then our last one. Ooh, I think I did this one. Did that one wrong. 0.187 is about right here. And then 0.047. So that's about a little less than halfway here. And there we go. So the probability, the small p for each trial was a little bit greater than 0.5. But because it's a little bit greater than 0.5, a majority of our values seem to congregate towards the right, which means the tail of the graph is stretching out towards the left. So this is actually going to be more of a left skewed distribution here. So again, consider a single binomial probability distribution with an n amount of trials and a probability of success on a single trial. Here's what the graph of the distribution tells us. Obviously, the probability of R successes for each R are from 0 to n. That are from 0 are the probability of R successes for each R from 0 to n. That's what this distribution tells us. If a graph is mound-shaped and symmetric, the probability of success is either close to or exactly 0.5. If the graph is skewed to the right, meaning that the majority of the values in our distribution are clustered towards the left side, the right side of the tail, the right tail of the graph stretches out. It's right. That means that the probability of success P is less than 0.5. But as we saw from this example, the probability was a little bit greater than P. So that means that we skewed this to the left. So the more skewed the right of the graph is, the closer P is to 0. On the other side of that coin, if the graph is skewed to the left, the probability of success P is greater than 0.5. So the more skewed left the graph is, the closer P is to 1. And again, that's because the majority of our data is starting to cluster towards the left if it's right skewed, so P closer to 0, and more clustered to the right, left tail stretches out, P is greater than 0.5. The probability is closer to 1. Now we'll talk about expected value and standard deviation of a binomial distribution. So again, the two other features that help describe the graph of any distribution are its balance point and the spread of distribution. So the mean, the expected value, is also known as the balance point of that distribution, and the measure of spread refers to the standard deviation. So again, the mean is the expected value of the number of successes. So let's calculate how to compute the mean and standard deviation. So to calculate the expected value, you just take n times p. That's it, just n times p. Now, the standard deviation is the square root of np cubed. Well, which also means that our variance is just np cubed. That's before we take the square root. So that's the variance of that random variable r. Now, another way that we can write this is in terms of the mean. So first thing I can do is I can calculate the mean, n times p. Well, n times p is also here. So in other words, I can also calculate the variance by taking the mean times q. And then, of course, taking the square root of that to find our standard deviation. So again, r is the random variable, n is the number of trials, p is the probability of success on a single trial, q is the probability of failure on a single trial. Let's go back to our Jimbo here. Out of 6 throws, what is the expected number of goals Jim will make, and what is the standard deviation of that distribution? So again, our expected value is n times p. Well, what's n? How many trials did he have? 6. What's his probability? 0.5, which is 3. So out of 6 throws, and if you're doing 6 throws and he makes about 50% of the shots he takes, of course it makes sense to say that his expected value is going to be 3. Well, if I look for the variance now, this is np cubed. Well, we already figured out what np is. That's 3. Well, what's the probability of failure? 0.5. That gives me a value of 1.5. And now, of course, to find the standard deviation, I'm going to take the square root of that 1.5. So square root of that number. I'm going to do 3 decimal places. I get a value of 1.225. This is my standard deviation. Here's another example. Old Friends Information Service is a California company that is in the business of finding addresses of long-lost friends. Old Friends claims to have a 70% success rate. Suppose that you have the names of 6 friends for whom you have no addresses and decide to use Old Friends to track them. What are the expected number and standard deviation of friends for whom addresses will be found? Okay, we need our n, we need our p, we need our q. So our n is 6 friends, n is 6. Our success rate is 70%, which means our q is 0.3. So our expected value is np, which is 6 times 0.7. Which gives me a value of 4.2. My variance is npq, which again, we've already found np already. That's the average. So that's 4.2 times 0.3, which is 126. And then our standard deviation is just going to be the square root of that number. .122. So we have an average of 4.2. We have a variance of 126 and a standard deviation of 1.122. Now, a good way that binomial probabilities and the mean and standard deviation work well with is quotas. Minimum number of trials for a given probability. So quotas occur in many aspects of everyday life. What are some examples when quotas can be used? Well, a lot of quotas are used in sales, used in manufacturing, all those kind of, there's plenty of examples where quotas are actually used. All quotas have one thing in common. We can figure out a quota by using the binomial probability distribution. Because either you meet your quota or you don't. Or either you meet your goal or you don't. So what we're going to do is we're going to look for an example. We're going to try this example of finding a minimum value of n for a given probability. So here's this. A satellite is powered by 3 solar cells. The probability that any one of these cells will fail is 0.15, and the cells operate or fail independently. So here's part 1. In this part, we want to find the least number of cells that the satellite should have, so that when we can calculate the expected value, it is not smaller than 3. So again, n represents the number of cells. R is the number of successful or working cells. P is the probability that a cell will work. Q is the probability that a cell will fail. And mu is the expected value, which we don't want to be smaller than 3. So what is the value of Q? What is the value of P? P is the probability that a cell will work, but that's not what we're given. We're given that the probability that the cell will fail, which is 0.15. So our Q is 0.15, which means our P is 0.85. The expected value of the number of working cells should be no smaller than 3. So we want our expected value to be greater than or equal to 3. So we want NP to be greater than or equal to 3. So we're going to solve this inequality for n, in which case all we got to do is divide both sides by p. And so n should be greater than or equal to 3 over p. Let's actually calculate that. What's our p? 0.85. So that's n greater than or equal to 3 over 0.85. 3 divided by 0.85, I get roughly 3.529 as the minimum value of n. All right, so since n is between 3 and 4, should we round it to 3 or 4 to make sure that we have at least 3? Well, if n has to be greater than or equal to 3.529, and we're talking about whole working cells, we really should round this up to 4. That way our expected value will be at least, or that way the average will be at least 3. So we definitely want to make sure that our average is at least 3. This will happen if our n is 4. So if we're doing minimum value of n, best practice is usually just to round up, is to always round up. So in this part, we want to find the smallest number of cells the satellite should have in order to be 97% sure that there will be adequate power. That is, at least 3 cells work. So the letter R has been used to denote the number of successes. In this case, R represents the number of working cells. So we're trying to find the number of cells necessary to ensure what? Do we want the probability of R to be greater than or equal to 3 is 0.97? Or do we want the probability of R to be less than or equal to 3 equaling 0.97? Remember, we want at least 3 cells to work. So at least tells me that I'm using greater than or equal to. So this is what we're using. We want the probability of R being greater than or equal to 3, to be 0.97. So that's what we want. So what we're going to try to do is we wanted to make sure that we want at least 3 cells working. So let's try a sample size of 4. Okay. So what we're going to do is we're going to have to do some guesswork here. Okay. Let's start with n being 4. So if r is greater than or equal to 3, that means that r can be 3 or 4. So the probability of r being greater than or equal to 3 should be p of 3 plus p of 4, because remember, they're mutually exclusive events. Okay. So we're going to do binomial PDF calculations with 3 and 4 to find the values of p of 3 and p of 4, with our small p being 0.85. So remember, this is binomial. This is binomial PDF of our n. In this case, it's 4. Our probability of success 0.85, and our x, whether it's 3 or whether it's 4. Okay, so let's find p of 3. So I'm going to go to my calculator. I'm going to do second variables. Scroll down to binomial PDF. My trials are 4. My value of p is 0.85, and my x value, we'll say, is 3. I get a value of 0.368475 plus. Now we'll do the same thing again, but instead of my r being 3, this time my r will be 4. I get 0.522006. Let's add these up. And I get a total of 0.890481. So I want a probability of at least 97%, or 0.97. That doesn't give us 0.97. So 4 cannot be the minimum value. 4 can't be the smallest value of n. We need to go up 1. We need to do 5. All right, so we're going to change this to a 5. I'm going to just erase all this. Okay. So we're going to change our PDF formula. So 5. And then this time my r would be 3. So I get 0. And this time I'm just for the sake of speed, I'm just going to round to 3 decimal places instead. 138. Let's see. For 4, I have 392, and for 5, I have 0.444. Okay. Now I'm going to add all those up. And I get a grand total of 974. I wanted the smallest value of n so that my probability is at least 0.970. Well, 4 gave me 0.89, which is not right, but a value of n gave me a value of 0.974, which is greater than this, but that's what we wanted. So 5 is the smallest number of cells that we can have to ensure a 97% chance that all 3 cells will be working. So no, n equals 4 will not guarantee that. But n being 5 does. Now, if you're trying to use the binomial PDF or binomial CDF calculations, you have to be able to read. You have to be able to read the problem as it's written and interpret it in such a way that you can find an accurate method to use your calculator. Remember, binomial PDF only works for an exact number of successes. So PDF only works for r equals something. CDF, as you see down here, only works for r being less than or equal to something. PDF and CDF do not cover greater than, less than, or greater than or equal to. You're going to have to manipulate your formula in order to, or manipulate the probability and use complements where necessary. So for example, if I'm looking for the probability of at least one success, that's 1 minus P of 0, because that's R greater than or equal to 1. At least 2 successes, R greater than or equal to 2, so that's 1 minus P of R less than or equal to 1. That's a CDF using 1. At least 3 successes, again, this is a CDF with 2. And then if I want at least M successes, then just subtract M from 1, or subtract 1 from M, and use less than or equal to on a CDF. So that's using a CDF, okay? And I mentioned this in 5.2. If I'm doing R less than M, just R less than M, then I can adjust this by doing R less than or equal to M minus 1 and do a CDF on that. If I'm doing R greater than M, again, I can go back to this, but instead I would do 1 minus R less than or equal to M. Okay, that's a CDF, because remember, I'm not including M. And if I'm doing R greater than or equal to M, I already showed that. Okay, so you have to pay attention to the wording of these probabilities that you're looking for and adjust your probability calculations accordingly.